chapter 12 after we try a couple of problems here. All right, so where I wanted to start today, Chemistry 3101, is with a few synthesis problems. And the first one that I wanted to take a look at, so this would fall under the umbrella of course, chapter 11, which is synthesis, of course. So the first one I wanted to take a look at is if you take this compound, so this is 1-bromobutane, and if you want to convert it into this compound where we have 1, 2, 3, 4, 5, 6 carbons, and we have a 3-membered ring with an oxygen in it here. Does anybody remember the name of this kind of group here? It's a type of functional group that we're going to look at. Yeah, it's an epoxide, right? So if we want to make, so I'll pencil this down. Thanks, everybody. So this is an epoxide. So if we want to make an epoxide, there's only one way that I taught you how to make an epoxide, one reagent. Does anybody remember that reagent that we need to make an epoxide? Yeah, thanks, Tiana. Awesome. That's awesome. It's MCPBA, so MCPBA, or if you wrote RCO3H, it's a peroxy acid is what it is. So Audrey, you're correct. Tiana, you're correct. Both perfect answers. Now, I have one more follow-up question then. If we make the epoxide using MCPBA or a peroxy acid, what's the functional group that has to be found in the starting material? So we take a certain functional group, we treat it with MCPBA, and we make an epoxide. Anybody have an idea what functional group that is that we need? It's not a ketone. No, it's not a ketone. It's an alkene. It's an alkene, exactly. So what that means is that we would need to have this alkene, right? And so now we've done one retrosynthetic step, and we've shortened the synthesis by one step because now we're just asking ourselves, well, how would we get to this alkene, right? How would we get to that alkene? Well, something that I didn't do at the very beginning was I didn't count the carbons. So in our starting material, we have 4 carbons, and in the final product, we have a total of 6 carbons. We have a primary, this is a primary alkyl halide, and I only taught you one way to add carbons to that primary alkyl halide. Could anybody provide me with the reagent that I need to add 2 carbons to my chain here? And you can unmute your mic and holler it at me, or you could just type it in the chat. Yeah, it's acetylide, isn't it? Absolutely. So sodium acetylide. So we write that like this. So here's our acetylide ion. We'll put in the sodium cation. And that's going to do an SN2 reaction, right? Just a regular old nucleophilic attack followed by loss of leaving group. And that's going to give us the alkyne. So 1, 2, 3, 4, 5, 6. So you have to count your carbons very carefully here. And then if we want to convert this compound into the alkene, does anybody remember? We learned 2 ways to reduce an alkyne to an alkene. One was sodium metal reduction, and one was hydrogen with Lindlar's catalyst, but only one of those works when I have a terminal alkyne, when I have a hydrogen on one side. Does anybody remember which one of them it is? Exactly. It's hydrogenation, isn't it? Right? Hydrogenation in Lindlar's catalyst. Right? That would give us the alkene. I'm going to just convert that into, I'll just change the color of it. So, oops, I didn't mean to do that. Here we go. Like that. There we go. We'll change the color. So there's our alkene. And then to convert that into the epoxide, like my students told me, you treat it with MCPBA, which is the same thing as a peroxy acid. So I'll change the color of that too. What do you think? Not too bad. So that's a total of what? 1, 2, 3 steps in that process. But I don't want you to lose sight of this functional group. And we're going to talk about this functional group in gross and dirty detail later on in this class, or in this. Yeah, I think it's in chapter 13, maybe. We get into epoxides in a lot of detail. But there you go. There's our first synthesis problem of the day. Another thing that I'll just mention here about Lindlar's catalyst, you might remember in the textbook, it mentions a little bit about what Lindlar's catalyst is. Do you remember another name for it? Sometimes there's another version of it called the P2 catalyst, right, which is just like nickel and boron together. Yeah, as long as it's a poison catalyst. But there are several different poison catalysts out there. There's Lindlar's, there's the P2 catalyst, there's nickel boron and things like that. But anyhow, they all do the same thing effectively. Anyhow, let's try another one. I thought this one was kind of an interesting question, so just bear with me as I pencil it down here. It was taking, so if we take 2,3-dimethylbutane, and if we try to convert that into acetone. So if we want to convert that into acetone. So I know we haven't covered the nomenclature of ketones yet, but this is the simplest possible ketone you can have, and this is called acetone, which is nail polish remover. So what's the first thing you notice here is that we're starting it with 6 carbons, and we only end up with 3 carbons. So if we're going to decrease the number of carbons, what's the only way that we know how to decrease the number of carbons in a skeleton? Absolutely. This reaction must involve ozonolysis, right? It must involve ozonolysis. And if I was to do a retrosynthesis from the acetone, and I'll just move the name, let's move that over here. If I was to do a retrosynthesis on this, you know, based on ozonolysis and what I taught you in Organic Chemistry 1 is if we could make this alkene, then all we'd have to do is to treat it with ozone in the first step and DMS in the second step, and that would give us 2 molecules of acetone, right? If you do the ozonolysis process, you can just erase the double bond like that and put an oxygen on each side. It looks a little bit ridiculous, but it shows you that you'd end up with 2 molecules of acetone. Give me a thumbs up if you follow me on that rationale of what I'm doing here, making that alkene. Cool. All right, good. So I'm going to go back to the alkene. And now what we've done is we shorten the synthesis, and we want to get from here to here. We want to take 2,3-dimethylbutane, and we want to convert it into 2,3-dimethyl-2-butene. So I have another question for you. If I'm starting out with an alkane, this is just a plain old alkane. What's the only possible set of conditions for the first step? Absolutely. Absolutely. So let's pencil that down. It's going to be bromine and light, and that's going to afford a bromination at the most hindered carbon, excuse me, like this. And now if I want to convert that to the Zaitsev alkene, right, if I want to convert it to this alkene, would I use a hindered base or an unhindered base? Unhindered base, absolutely. So I'm going to choose, I'll choose sodium methoxide just to be cheeky. We usually pick ethoxide. It's a fan favorite. That's right. Thanks, Chaylin. And so now all I'm going to do is treat that with ozone, first step, and DMS in the second step. And there we have it. That's all there is to it. All right, just keep in mind that, you know, if you were to use a hindered base here, like potassium T-butoxide, that would give you the Zaitsev alkene, right? That would give you this compound, and that's not the compound that you want. You want to get the Zaitsev alkene, not the Hoffman alkene. My mistake. All right, let's try one more synthesis problem. There's another one I wanted to look at. Yeah, let's go with something in the same vein as the last problem. This one's got some similarities, but I thought it was a good problem. This one here, good problems to have, right? Problems in organic chemistry. All right, so what if we wanted to make this compound? Here's one for you, where we have a nitrile in the compound. When was the last time we talked about a nitrile? Not a whole lot, right? So if you don't remember this functional group, this is called a nitrile functional group. And I think the reason I chose this problem today is that I think this is a really good demonstration of you know, it might bend your brain a little bit at the beginning, but I think if we take a step backwards, if we think in terms of retrosynthesis, hopefully you remember that you can use cyanide, CN-, as a nucleophile. This is something that was covered in detail in chapter 7. And all I'm getting at is this: if you could add a bromine out here, then all you would have to do is treat that compound with sodium cyanide, and that's just going to do an SN2, nucleophilic attack, loss of leaving group, and you're going to end up with this nitrile. So you're going to end up adding the nitrile group on there. So the question is now, you know, how do we get from here to here? And my students just told me that the only possibility is to treat this with bromine and light, and that's going to put the bromine not in the position we want, but it's going to be 1 carbon away from it. However, we just saw that if you treated this with a big old hindered base like T-butoxide, that's going to pull off one of these protons on this beta carbon, right? Here's our alpha carbon, here's our beta. So that can abstract this proton in order to give us this alkene. Oops, the Hoffman alkene. And so now my question for you guys is, if I want to take that Hoffman alkene and I want to put this bromine on the end like this, could anybody tell me the set of conditions I would use to do that? Absolutely. Absolutely. You guys are faster than I am, right? It's bromine and peroxide, right? We want to do an anti-Markovnikov addition of bromine. So this is anti-Markovnikov addition across that double bond. And that gives us the primary alkyl bromide. And then in the last step, we treat it with sodium cyanide, right? Cyanide is a nucleophile, and that's going to do the SN2 reaction. I'm just adding some mechanisms in here. And there you go, folks. So that is about it for chapter 1. I just want to go back into the slides quickly with you and just point out a couple of things. So the first thing, if you're, rusty on your organic chemistry, is I'm on the wrong file here. Here we go. There we go. That's better. So if we go back in here, the first thing is that you want to know these reactions frontwards and backwards, right? You need to know all of the alkene chemistry without any kind of doubts or anything. You just need to know it. I don't know what else to tell you other than that. You need to be very aware of these reactions. The same thing here. You need to be aware of all the reactions that we used in the alkynes chapter. So that would kind of be your baseline, I would say, for the first quiz of the semester, of the summer semester. And then another thing that I want to point out to you is make sure you read the section on green chemistry. I put skip on it, and that's because we don't ask a lot of questions about it, but I'm going to change it to read it. I think it's worth reading. It is 2023. I think it is pertinent. I mean, we all want to be responsible global citizens. And so I think it's a wise thing to read this section. It's very, and trust me, it's very short. You can read it in 5 minutes. But, one thing I just wanted to point out about the use of safer solvents, because I know I had a bunch of you as students in the lab last semester. And so when I was a student in the 90s, in terms of solvents, we used to use dichloromethane all the time as students. Okay, so this is methylene chloride or dichloromethane. They both mean the exact same thing. And basically, what's really changed in organic chemistry since I was a student is back in the day, we used solvents that had chlorine in them constantly. Like dichloromethane is one. Another one is chloroform, and I'm sure you've all heard of chloroform. It's used for kidnapping. Anyhow, so I'm kidding. It's used for different reactions. But anyhow, so chloroform is another chlorinated solvent. And even worse than that is carbon tetrachloride. Even when I was a student, it was a hard thing to get your hands on some carbon tetrachloride. So any solvents that have chlorine, we consider those to be pretty nasty for the environment. And so we always try to avoid using any solvents with chlorine in them. Now, you might follow up with a question like, well, what do you replace them with, Mr. Dion? That's a great question. And it really is, it would be a case-by-case scenario. But just to put the bug in your ear, scientists are always trying to find ways to avoid using chlorine as a solvent. Anyhow, and then when we talk about atom economy, I went over this last class with you a little bit. The whole idea behind atom economy is nothing more than we want as few atoms in the garbage as possible, right? Nobody who's hearing the sound of my voice wants to pollute our planet, and I certainly don't. And so anytime that we can find a way to do any kind of chemistry where we avoid putting atoms in the waste, we consider that to be a good thing. All right, so that finishes chapter 11. And as far as making your own synthesis problems, I'll leave that up to you. And just one last thing I guess I'll say about this class. So this would be kind of a departure from Organic Chemistry 1. So you're going to find as we move forward in Chemistry 3111 that if you're studying with friends, that it's going to happen all the time where you're going to find more than one correct answer, okay? However, my students will sometimes ask me, well, is my answer more correct than this answer or something like that? And here's a good way to phrase it. It says, in general, chemists try to find the most facile synthesis. And so let's say, I'll just use some students who I know really well. Let's say Audrey comes up with a synthesis that's 4 steps, and then I come up with a synthesis that works, but it's 10 steps, I would give hers a higher grade, right? Because we want to avoid doing as many reactions as possible. You want to try to minimize that kind of thing. Anyhow, so what would you call that? Work smarter, not harder, right? Anyhow, there we go.